Hi, everybody. How are you doing? We'll start in about 4 or 5 minutes, so let's wait for everybody to get on.
No, the
Do you have any questions before we start? No questions? We have no school on Monday next week because of the Labor Day. So if you have other classes on Monday, we don't have class session on Monday, Labor Day, okay? Oh, also, I got an email from one of the companies in Riverside today. They're looking for IT people. There are 10 positions available. This is a part-time temporary. I'm trying to find out a little bit more about how much they're paying. But if you're interested, if you have some background in computer maintenance, technical support, things like that, if you want to pursue it, send me your resume and I'll take a look at your resume. And I will give you more information once the company get back to me, but I just got an email today. So. Okay, we'll start in a minute. Make sure we download Unit 2 notes, which is Chapter 2 and 3. And then also we're going to go over the assignment together. Okay, I'm going to go ahead and get started. I think I just made a quick announcement earlier if you just got on. I have a company that's interested in hiring technical people, doing IT support, help desk, technician work. It's a warehouse, but you're mainly going to do technical work. It's a part-time position for 10 people. They reach out to me because I'm teaching technical courses. If you're interested, if you have background in system maintenance and you wanted to get some experience, send me your resume. I'll take a look at your resume and I'll let you know. And I will forward the resume to the manager that's hiring. I think they have urgent needs. And it's in Riverside, not too far. And you have to physically work there because that's what they need right now. And I don't have much more details than the 10 positions in IT. I asked the manager to give me more information, so I'll let you know further. Okay. All right. So today we are going over gates, and we're going to touch a little bit on logic gates. Some of this sound familiar to CIS7 if you took CIS7 with me, but we're going to expand a little bit more, and we're going to work with your general gates and, or, and not. So to start, if you have downloaded the notes, you can follow along. I just uploaded some additional information about transistors. So I'm going to go into screen share. If you have any question, just unmute and ask, okay? And I'll reserve some time at the end for questions. So we are going to touch on logic gates, and this is important for computer science and engineering. From the development side, we see a lot of this when we are implementing conditions, especially when you're trying to specify criteria in your loops or in your if conditions or if else statement. So what's really translated in the back, as we touched on binary last week, is we are going to look at how the processor actually look at these gates, okay? So at the high level, we are going to look at the microprocessor, which is your CPU. And the compiler, when it takes a look at the C++ program, what it does is it builds the entire program before it executes all the functions and all the objects that you have implemented in the program. Now, in digital circuits, what we see is that digital circuits consist of gates, which are basically transistors. So think of it like a switch, and when we're saying switch, we're really looking at the voltage that's entering and exiting, or the voltage that's introduced, which is 5 volts. So normally when you're getting a 1 as a signal is when it's going to peak at 5 volts, okay? And when you're getting a 0, or we refer to that as off, then the voltage would drop to 0 or close to 0. So it says right here that transistor is really a digital switch that's established either a connection, which is a close, or a break, okay? So when it connect or disconnect, so think about the light bulb. When you connect the light bulb, right? And if that signal is on or you have power, then that light bulb is turned on. So on the left-hand side here, this is just an illustration on how that would look like in 2D level. So on the left, this is considered open, and on the right, which is closed. So when it's open, then it's push. That means that when it's pushing, that means that it's connecting. And on the right, when it's closed, right, then that means that it disconnects. So when we're looking at transistors, what does that mean? What does it look like, right? So for the transistors, oh, I forgot to include the picture in here. Give me 1 second. Let me insert the picture real quick so you can see. Now, if you're working with Arduino or smaller electrical boards, right, micro boards, you would see that you might have come across transistor to really regulate the electrical signal coming into your breadboard, right? Or if you're connecting something directly onto the Arduino itself. However, let me find my picture so I can show you here. Sorry. So this is some of the common transistor that you see. They come in different sizes. So if you work with Raspberry Pi Arduino, you might have seen these. And sometimes they could be soldered on, or sometimes they could be plugged into the breadboard. So what we see is this is what the transistor would physically look like. And then in the microprocessor in your chip or your CPU, it's actually tiny microscopic transistors. So what you have is it would be integrated so that way we can implement, right, on the development level, we can write instructions to be able to include conditions for our program. And on the engineering side, you would see this is being made of semiconductors, which is silicone, and that's incorporated inside the processor itself. So in 1954, IBM replaced vacuum tubes because that's how we were using the system back then. Was computers were actually made of vacuum tubes, and they replaced it with 2000 transistors. And then today, ICs, integrated circuits, and also your MOSFET, which is transistor, is still being integrated in your processor today. So in 2016, we were looking at 7 billion transistors in some of the processor. And then I just wanted to share with you what it would look like today. So if you're playing your Xbox, the next time you play your Xbox, you should know that it would be made of so many certain amount of transistors. So this is a quick Wikipedia chart, so it gives you the overall. So let's look at the beginning, right? So if we're looking at some of the Intel processor early in the 70s, we're looking at approximately 2,000 to 3,000 transistors in counted MOS transistor, semiconductor inside the processor. In the later years, if we're going forward into the 2020 or 2019, so some of you are familiar with the Ryzen, AMD Ryzen, right? That's one, and not 7 or the 9 or even the EPYC. So we're looking at trillions of transistors that's inside, approximately close to 10 here. And it seems based on Moore's law, it's going to double every year. And also transistors can be implemented into memory, right? And what you see is in the cache of the processor itself, all of this can be incorporated in the engineering. So now, if we're going back to maybe the Xbox One, which is a little older, right? So as you can see here, the Xbox count for the transistors here, that's in 2013. And then if you're using iOS or Apple phone, right, like the A8, okay, which is for the iPad, here's the transistors count. It's 3 trillion. So with the quad-core i7 and the dual-core i7, we're looking in the trillion of transistor count. So what you see today is the basic concept on how gates is implemented, and think of gates as how transistor would be incorporated in integrated circuits inside the processor. So you're in your processor looking at your program, how is it going to be determining based on 0 and 1s and what you implemented in C++ as the double ampersand as AND condition, or the OR condition with the 2 pipe, right? How is that seeing what does it see as far as the and, the or, and the not? And not, we talked about how that was the first complement in the two's complement last week. So now I'm going to go back to the notes here. So in the logic gates, the first three logic gates we're going to talk about is the and, or, and not. And basically it's a construct of the circuits, and how that can be incorporated is on the binary level. We can introduce inputs to get some kind of output, because that's the purpose of the computer, is to take in input or some kind of value, and then to calculate and then give you the output, which is the result. So in the AND gate, it's always going to have two input. So it's going to determine based on the two value that's being pushed or input. And so that way it can look at those value and incorporate those value to give you the output. So when we have a 1, that means that it's going to have a positive 5 volt as an input. When we have a 0, then it means that it's going to have a low voltage or a 0 volt, as I mentioned earlier. And based on this, what you have is when you have a 1 that's pushed, it's going to cause it to close, and it's going to supply a 1 as the output. Okay, so when you have a 5 volt coming in, you're going to have a 5 volt as a result. When you have a 5 volt and a 0, you're going to have a 5 volt. So, and this is what we constructed as a truth table with the 0 and 1s. So in physical and the logical, we interpret on the logical side would be the binary equivalence. 1s for the 5 volt and 0 for the 0 volt, which represents high and low. So in corresponding, you would see diagrams that would use something like this. And when you see the D shape like this, you know it's an AND gate. And the AND gate would always take two input, A and B, okay? And then it's gonna have one output. So in the logical diagram, what we can see is that we can say, okay, if A is 0 and B is 0, when I have a 0 volt and a 0 volt, I get a 0 output. But as the description said earlier, anytime that you have a close, which is a 1, when you have a 0 and a 1, you get a 0. Okay. So when the AND is that when it's pushing that 1, it's going to close the circuit, then you would get a 0. With the A and B are 1s, it's either one of those are 1, but if one of them is a 0, we get a 0. If you have a 1 and a 0, you get a 0, a 1 and a 1, we should get a 1 at 5 volts. So with the AND gate, what we see is that we would have, anytime you have a 0 in the mix, you get a 0 as the output. Okay. So now let's do the first exercise. So here's the truth table again. And in discrete math, we would use the upside down V to indicate AND. And in C++, right, when you write the AND, it is the double ampersand, right? You can say if, right, this and this, then what's going to happen? You're going to have some kind of, you can have it C out, or you can do some calculation there, etc. Okay. So let's look at number 2. So when we have a 0 and a 1, we get a 0. A 0 and a 0, we get a 0. A 1 and a 1, we get a 1. A 1 and a 0, we get a 0. A 0 and a 1, since there's 0 in the mix, we get a 0. A 1 and a 0, we get a 0. And this is not addition. This is using gate, right? A 0 and a 1, we get a 0. And a 1 and a 1 is a 1. So you simply have 2 input here, and your output is 0 because there's a 0. When you have 2 0, you get a 0. When you have a 1 and another 1, you get a 1. So if it's true and true, you get a true, right? You get a 1 and a 0. When it's true and false, you get a 0. Okay? You get a 0 and a 1, you get a 0. So as you go through this, you can use the truth table and be able to have the output. So this is our output when we have this binary value and this binary value. This is our output. Okay. Any question? Okay. So we simply use the 2 input. So let's try this one. 1 and 1 is 1. 1 and 1 is 1. 0 and 0 is 0. 1 and 1 is 1. 0 and 0 is 0. 1 and 0 is 0. 1 and 1 is 1. 1 and 0 is 0. So when we have this input and this input, we have this output down here. So you simply take those 2 input to get the output. So we need to know the AND operation for our quiz and our test. So you're going to see something similar to this on our quiz and our test. Any question? Okay. So no question on AND. So the next gate is OR. Okay. And also with the OR gate, we would need to have 2 inputs. As long as one of them is on, it's going to be on. So if you have a 1 in the mix, then it's a 1. And sometime it will be drawn like this, where it's open. Or in some diagram you should see, so it looks like an arrow where you have A and B as input, and then you have 1 output. So you will always have 2 input for gate AND and gate OR. So as you look 0 or 0, you have a 0, 0 or 1. There's a 1 in the mix, so you get a 1. A 1 or a 0 is a 1. And a 1 or a 1 is a 1. So with the OR gates, as long as there's 1 true condition, 1 true input, 1 5 volts, it's going to give you 5 volts. So this is the OR. So let's do our next question. So we know that in number 4, it asks you how many inputs will yield on, right? How many inputs will yield on output? So you need to have at least 1 input to yield on. Because anytime that you have a 1 in the mix, you would get a 1 as the output for the OR. So in the AND, the difference is that AND, anytime that you have a false, anytime you have a 0, right, as one of the input, then you get the 0 as the output. The only way that it would be true or on is if it's both 1. So in some of your program, you would write if A and B, right, then A and B has to be true in order to get a true output. Okay. With the OR condition, if you write if A or B is true, so if A is true and B is not, it's still going to give you a true. Okay, so, and I see that sometimes students have issue with that because they don't see the difference between the and the OR at the programming level. But if you understand it at the gate level, you should be able to determine how it's going to be as the next part of your program, because you would know that the output would be either true or false based on the and the OR that you would use. So in the OR rule, discrete math, we use the V as the indication for OR. It's just a symbol that they use. So that would be the same as the table that you see in the notes. So let's find the logical output for this. Let me move this to the next page. So for number five, we simply go from the right, 1 or 1 is 1, because there's a 1, they're both 1, so you're going to get a 1. True or true is true. 0 or 0 is 0. 0 or 0 is 0. 1 or 1 is 1. 0 or 0 is 0. 0 or 0 is 0. 1 or 1 is 1. And 1 or 1 is 1. So what can we conclude by looking at this problem is that if you have identical value and you OR it, you're going to get the same value. Okay. Any question? Okay. No question? Okay, let's do number 6 together. Let me move this up so you can see. So in number 6, we repeat the same process. Find the logical output for this value or this value. Okay, so 0 or 1, we get a 1 because there's a 1 in the mix now. 1 or 0 is a 1. 1 or 1 is a 1. 1 or 1 is a 1. 0 or 1 is a 1. 0 or 0 is a 0. 0 or 1 is a 1. 1 or 0 is a 1. So as you see the inputs, anytime that it has a 1 included, either, right, or both, we would have a 1 as the output using OR gate or the OR operator. Okay, any question? So again, we need to know how to do and or at binary level, right? For quiz and tests. So for quizzes, you do have 3 attempts and the highest score is going to record, and there would be a quiz coming up after next week. I will have quiz review. Okay. So as some of you get into like, so if you go into engineering, you would have to take, you know, digital logic courses or digital circuit courses. Then you would get more in depth in with the electronics and tie with the computer, right? How computer design and system design and engineering would be. And then for computer science, you might touch on the concept in various classes, especially architecture classes.
I'm sorry, I have a question.
Sure.
Can you explain again the difference between being pushed and on, please?
So for the push, I think that the way that the textbook is describing this can be confusing, right? So when it's open, right? So here you see open and close, right? So on the left, it's open and it's closed. But when it's pushing, technically, when you have this right here, established is when it's connecting, when it's getting electrical signal. When it's closed is when it's not, okay? So we probably think that, oh, when it's open, then we would have a 0. That's not true, okay? So on the right switch, when it's closed, even when it's pushed, when it's a complete loop, it's closed, it's a closed circuit, then it's a break in the circuit. So when you switch off your light, what happens is you break that signal from the rest of your, you know, household electrical system, correct? So technically that would be off. So you close out that circuit. When it's open, then you can have 5 volts introduced and it would flow through. So even when it's saying it's pushing on both sides, so when it push on this and it would close out that circuit, it would have it turn off, compared to when it's pushing the other way. When you think of it, when it's pushing the other way, it actually opens up that circuit. Okay, so think of it like this is pushing from this side, the under, and this is pushing from the upper. Okay, so in the normal close, it's pushing from under, it would close out that circuit, so it breaks it off, turn it off. Where it's pushing through from the upper, it's pushing to the upper, then it opens that circuit, and then you would have a flow of 5 volts. Is that okay?
Yes, it makes sense. Thank you.
No problem. Okay, so as you can see there, it would be out. Let's see. All right, let's talk about NOT gate. So we got a little bit of NOT when we did the flip bits in the first complement, or the one complement of the two's complement last week. Now, unlike the OR and the NOT gate is unary, meaning that it doesn't require 2 inputs, it just needs 1 input, right? And what happens is this would be normally closed in variety, so it breaks the connection, so it's pushing from under to close out that circuit, like this, okay? So now, you know, if you think about mathematics, right, you're like, well, is it like an inverse? So yeah, it is the opposite. So when you have it, the signal as off, when you NOT it, it peaks at 5 volts, so it turns on. When you have the signal as on, it's going to drop down to 0 when the NOT operator is applied. And the NOT you often see in diagram for gates, it's a little triangle like this, and often it has a bubble right before it's out. So what happens is you would have a break in the circuit. So here, when we have a 0, then if it's not A, then it's going to yield a 1. When we have a 1, then we're going to yield a 0. So now, before we get to Nand, sorry, let's go to our assignment. So describe the NOT gate with the input. So it only requires one input. Output will be the opposite of input. So when we have a 0 as input, the output is 1. When we have a 1 as input, the output is 0. Okay. And in C++, we use the exclamation point, correct? Not when something is not equal to, then it could be any outside of it. But let's say if I have something that's not equal to 0, it could be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, or 100, right? So what the computer does is, and we're going to get into Venn diagram and some of that later on to really apply the development concept with it. But in the NOT rule, if we're just looking at 0 and 1s, because there's only 2 options, it has to be the opposite, everything else, right? So if it's not 0, what's left? It's 1. Okay, if it's not 1, then what's left? It's 0. So, and sometimes you would see it as using this symbol. Okay, it's like a negative sign with the drop line there. Okay. So when we look at number 8, we would start with the right. So when you have 1, not 1 is 0. When you have 0, not 0 is 1. Here we have not 1 is 0. Here we have not 1 is 0. Here we have not 1 is 0. Here we have not 0 is 1. Here we have not 1 is 0. Here we have not 0 is 1. Here we have not 1 is 0. So it's just the opposite. Okay. Any question? Okay, next question, number 9. Again, we would flip the bits, or the output will be the opposite. So not 0 is 1, not 1 is 0, not 0 is 1, not 1 is 0, not 0 is 1, not 1 is 0, not 1 is 0, and not 0 is 1. Any question? Okay, so at the basic level, we have and, or, and not. Now we're going to have combination of the operators or the gates. Okay, so in the NAND gate, we simply the first operation is it's going to AND it, and then it's going to not. So basically it's AND not. Okay. Now, if you not it and then AND, it's not going to work because not requires only one input. So you first have to AND the two values together, get one output, and then you not that output to get the NAND output. So it's the opposite of the AND gate, meaning that we AND everything together and then flip it. So an AND gate can be constructed from, the NAND gate can be constructed from the AND gate output is attached to a NOT gate. So when it's drawn, you would see something like this, which is our AND gate, and then you add the little bubble, which gives it a NAND gate. Okay, so it simply have two operation. It would have AND, NOT. So now this is the simplest logic construct of transistor, resistors, wire, etc. And this is commonly introduced. So NAND gate is logically complete. So what you have is A and B, and then not A and B. Okay, so 0, NAND 0 is going to give you a 1. 0, NAND 1 is going to give you a 1. 1 NAND 0 is going to give you a 1. 1 NAND 1 is going to give you a 0. Okay. So in the next question, it asks you, compare AND gate to the NAND gate. Note the differences between these gates, right? NAND gate is the opposite, I should say, NAND gate output is the opposite of AND gate output, which is that we would not after AND. Okay. So we would AND the two input values, and then we would take the output of the AND and then NOT it. Okay. Any question? So here's the table again. Let's look at this, right? Now, a way that you can do this, I'm going to handwrite it real quick so you can see. So if we have 1, 1, 1, 1, 1, 0, 1, 0, 1, right? And we have 0, 0, 1, 1, 0, 0, 1, 1 like this. And we're supposed to do the NAND. So to start, what we can do is we would AND these guys first, and then we would NOT it. So we simply would have 1 and 1 is 1, 0 and 1 is 0, 1 and 0 is 0, 0 and 0 is 0, 1 and 1 is 1, 1 and 1 is 1, 1 and 0 is 0, 1 and 0 is 0. So this part is the output of AND. Then what we do is we would flip the bits, or we would NOT this. So the next part is we would NOT this. So we would have 0, 1, 1, 1, 0, 0, 1, 1. Now, you don't have to use the table. This is a manual way of doing it. Or if you use the table, then you can also look at what the output would be with the two inputs. Okay? Any question? All right, so we can do the next one. For number 12, you can try. So first you can AND them together, and then you would NOT it after you got the output from AND. So first we would AND these to get the output first, and then we would NOT it. So 0 and 0 is 0, 0 and 0 is 0, 1 and 1 is 1, 0 and 0 is 0, 1 and 1 is 1, 0 and 0 is 0, 1 and 1 is 1, 0 and 0 is 0. So anytime you AND the identical, you would also get the identical or the same result as the input. Then now we would NOT it. So we have 1, 1, 0, 1, 0, 1, 0, 1. Any question? So similarly, we would see that with NOR, which is NOR is not OR, right? In your notes, it talks about NOR gate here. It's the opposite of OR gate. It says that it is on if only and only if not the case at least one of the input is 1. NOR gate is constructed from OR gate whose input is attached to NOT gate. So after we OR it, we would apply NOT to get the complete output. So there are two operations there. Okay. So going back to our assignment, we can say that NOR gate is opposite of OR gate. Result, it is NOR is not. Okay, so we would OR and then we would NOT it. Okay. So now if we do the number 14, so 14 we have the first value as 1 1 0 1 1 1 1 1. And then the second value is 0 0 1 0 0 0 0 0. So first we would do the OR, which is anytime that you have the 1 in the mix, it's a 1, 1 or 0 is 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 1, 0 or 1 is 1, 1 or 0 is 1, 1 or 0 is 1. Then after this, we would NOT it. Then we would get all 0. Any question? Okay, you try number 15. So first you OR the two value, and then once you get the result, then you not the value, the result. Any question? Okay. So as I didn't include exclusive OR in this, it's very brief, so I want to share with you a little bit on what it's really for, right? So XOR or exclusive OR gate, it's represented in the truth table because it's a way that, well, it's used in binary arithmetic it's a way that we can create an adder. Just like how when you add the binary last week, you have that carry one, right? That carry one has to be implemented somehow with the gates. So that way it would be able to move to the next column and applied in the addition, or when you're doing subtraction, when you borrow one from the left column, how that's going to be utilized. Okay, so exclusive OR is a way that we would look at how two bits are being added and what the bit that's being carried into the next the next position bit. Okay, so if we're looking at a byte, how we add that carry to the left side of it, which is the next position of the significance in that byte, because the least significant is on the right, and then we move it to the next position, which is it's going to become a little bit more significance in that byte as the position of the bits. So this is used to be able to implement carry, or what we call that as the adder, when you have the two bits. Okay. So now I have added a little bit more notes. I didn't have time to make the adjustment to this, but you can see. And sometime when you're working with XOR, like in a lot of the times when you're looking at like the assembly level for cryptography, a lot of the time you see with the XOR or the exclusive OR, is that it's going to give you, it tells you here that it's a digital logic gate that gives you a true 1 output when the number true input is odd. So anytime that you would have the 1 as a 1 input, right, then you're going to get a 1. But if you have two 1s, then you're going to get a 0. So anytime if you have a 0 and a 1, you're going to get a 1. Okay. So if you look at this, this is the same as addition in binary, right? We have a 0 with the carry 1 to the next one. So this looks like the addition output in when we add the binaries. And it's also viewed as addition mod 2. So it's used to implement addition in binary, and when you apply multiplication to, you know, when you try to multiply numbers in your calculator on your computer, on your smartphone, ultimately that's still addition in the back. It just applied that many times, so it goes through the loops, right? So if I do 2 times 9, I'm just adding 2 9 times. So it's just adding, and when the computer does it, it breaks it down into binary and it does the addition 9 times. So it loops it 9 times. Okay. Any question? Okay. So here is a little bit more information, and also used in subtracting and also used in control inverters and such. So this gives you a little bit more, but the takeaway from this is it's being used in carry, and the output for the XOR is same as the addition for binary. Okay. We completed 15. I'm going to go to notes now. So this is the diagram, how it's drawn with exclusive OR. So with the NOR, you would have a bubble in the front right here, but with the exclusive OR, you have a little line drawn like this, then we would know it's an exclusive OR. With the half adder circuit with the truth table, it's going to break out to be the AND over here. Okay. Any question regarding to chapter 2 with gates? That's mostly review for many of you. You've probably seen truth table many times in your programming classes as well, true false. Okay. So we touched on this. This is generally just review with the truth table for the beginning part of chapter 3. Okay. I want to get further down when it's going to go into conjunction and disjunction, I guess. Let's improve with different type of math law there. Okay, so let's talk about conjunctive normal form and disjunctive normal form. I try to edit this because students always get a little bit confused about how this is written. So in conjunction, you would have the clause with the AND inside here. Well, each of the clause is the disjunction, the disjunction of the variable. What does that mean? Okay. So we can have something like this. Okay. So in the conjunction, you would use the operator and the operator or. Okay. And how it's going to connect is it's going to connect it with the and. Okay. So you would have A or B and C or D. So you can also have A or B and not C or D. Okay. So you notice that it's going to connect one term with another term with the AND operator here. Okay. Any question? Okay. So the way the book writes this is they're using this right here. So you notice A is one term, it's AND, not B, and B or C. So the way that it would be accepted is that the OR has to be within the bracket or the parentheses. It has to be treated as one output already. So we would output this, then we would AND it with the not B, AND it with the A. Okay? Similarly here, so you would have the complete term or the output within these three. Okay, so with these three, you would have one output. After that, you would AND it with another term, AND it with another term. Okay, so this you have A or B or not C, and not B or A or D, and F or not E. So with the conjunctive normal form, you would always have the AND to connect the terms together. Okay. So before we get into, so yeah, I didn't like it how the textbook shows this because it confuses the student when they throw the disjunction in there. Do you have any question?
Can you
Okay.
explain that one more time?
Okay. So in the conjunctive normal form for the Boolean, you would use the AND to connect the terms together, whether it's a combination of operators within. So in this case, we have B or C. So think of this as numbers, right? Like B could be 4, right? And then we convert it to binary, or C could be 5 converted to the binary. So B or C, and then you would AND it with not B, AND it with A. So to connect the terms together, so here you have 3 separate terms, and in order to be conjunctive, meaning together, you have to use the AND operator. Okay. Now, in this case, the OR would only exist within the parenthesis, which get operated first. It's going to take that output and it's going to AND it with the other term's output. Okay, so think of conjunction is together with, right? And so we would want to AND the terms together, and inside each term it can be OR. Okay, now this is an OR because it treats it as it treats it as one with another and as one term. Okay, I didn't like how they use it like this because it confuses the students when they look at that. But what I want you to take away from this is if you have each term like A, not B, then you would AND them together to get the conjunction. Okay, CNF, conjunctive normal form. So in this case, we have 3 terms. Okay, now with this, it can have, with the clauses A, right, and not B, and B or C. So first it's going to do B or C first, and then it's going to AND it with the not B, AND it with the A. Okay, and in this case, it's going to do A or B or not C, get an output, and then it's going to AND it with this term output, and it's going to AND it with this term output. Okay, so what that gives us is the logical equivalence when you have different logic gates that's going to be combined. One that's going to be OR within to get that entire term, and then it's going to AND it with another term to make it a conjunctive. Okay. We'll come back to some De Morgan's law when we talk about Venn. So let's look at this question. So in the basic operators that represent conjunction is that with the CNF, you would have an operator connecting the terms, or operator is used within the term. meaning inside to get an output for that term. Okay. And going back to this, you see that, I'm sorry, I'm looking at disjunctive. You see disjunctive, we have and for each term and then or within the term. In disjunctive normal form, which is when we would use the or for the clauses, so we would use for the variables, so in each of the term, it's going to and together first, get the output, and then it's going to or it with the other terms. So what do I mean? So right here, right, inside the parenthesis, it's going to use the and. Get the output for this, then it's going to or it with the not be. So it uses the OR gate to connect the terms together, one variable with another variable, right? And within the variable, within the terms, it's going to use the OR gate. Okay, so we can define that. In the disjunctive normal form, OR operator is connecting the terms of the variables, we can say, and then the AND operator is used within the term. Any question? Okay, no question. So for our, we're going to do the exercises after we answer that question, but for our quiz and test, right, it will give you a question where it would say this and this, or this and this. Is this a conjunctive or a disjunctive? And you have to determine. Okay, so make sure you know the difference between the two. One uses and, disjunctive uses or. So the conjunctive uses and the disjunctive uses or. And the conjunctive use or within the term, and the disjunctive use and within the term. So in the case where if the terms are and then the variables are or, right? Inside when it's or, and then outside it's and, then it's a conjunctive. Okay, where it's the other way, when inside it's and then outside it's or, then it's disjunctive. Let's see. So in the case where if you have the complement, that just means that it would represent that as negation, right? Like not be. Okay. So in that case, the negation will be applied to each of that term. No parentheses is needed. So let me see if there's, okay, not in CNF. Okay, so in this case, you would have it applied to, with the negation right here, that will be, it's not CNF, where it's the opposite of the CNF. Okay. So let's answer the negation. Not operator is used for CNF or DNF. Okay. So we have this right here. It says not X or Y or Z, and X or Y or not Z. Is this a CNF or a DNF? What do you think?
CNF.
CNF.
Yeah, very good. So conjunctive, normal form, aka CNF. Why is that? Because it is or operator is used within term or variable, right? And then an operator is used to connect the terms, meaning connect the variables together. So you would see something like this on quiz or test. And then if we apply the not, the negation, simply we would apply it outside here to negate the entire CNF or the C. So basically you would have the output of the conjunctive normal form, then you would negate it. Okay. So, and going back to some of the math law, right, you would see that with distributive law, this is also proven. With associative law, this is also proven. And so this is why the author, she listed all the appropriate math law that would apply to how this proof would be with the gates being used, CNF and or DNF. Okay. All right. So now for 18, so we have not P, right? So this is not P, and then or, I'm sorry, yeah. And not Q, right? Or R. So what is this right here? Is this a CNF or a DNF? So here we have a conjunctive normal form. It's using or on the inside, right? But this one uses or on the outside as well. Can it be a conjunctive normal form? Or is it a disjunctive normal form? So here's conjunctive normal form. What do you think? It cannot be conjunctive, right? Why is that? Because it has this right here. Is this disjunctive? Let's go look at disjunctive normal form. So here's disjunctive normal form. Can it be DNF?
No.
Why not?
because of the and parentheses?
Yes. So inside with the variable or the term, right? So it's neither. Okay. It doesn't meet the criteria for the DNF or nor the criteria for the CNF because you have a mix there. So none. Sorry, where was it? Right here. Yeah, so you have this on the outside and this on the outside. So we can say not. See, we should say it is not CNF or DNF. And we don't mean negate it either, right? It's not meeting it because it's because of this right here. So we say that and or operator are used to connect terms. So it's neither of the option. It's not CNF or DNF for AT. What about 19? So I clipped this right here to show you. Does it look anything and like the clauses in the formula? It is close to this one, but in the exception that it is close to this one. An exception that it has these two right here. Does it meet the criteria? So everything else, so what we have is we have this on the inside and on the inside or on the outside. But when it gets to here, it changes. Does that meet the criteria? Look at this, right? Where we would have, if we treated this as separate variable, will it be able to meet it? This is a DNF. Do you know why? Because this is an individual, it's a negate of the actual variable, right? So in here, what we have is inside the term, we and it and then we or it on the outside. Then over here, when we have it, it can be or out here with the negation, just like how we have A or B here or negative A or B, then we would be able to have it as a DNF. Okay. Let's see. Like how you see that here with the B. Okay. Any question? So this one is a DNF, right? Within term and operator is used within term or operator is used to connect term. And then we have the or operator is used to connect the negated term. Or is it the and? Hold on. Yeah. Actually, I'm sorry. I think this one is not. It's not a DNF. So it's neither. Right here. Because of this right here. And
If
then
the,
this,
Q and R was in parentheses,
yeah, that would work.
it
You're
would work.
correct. Yeah, it's because of this right here. But if you have it and, that would work for CNF. So now this one, because of this part right here, I'm gonna highlight the section where it should be. You should look at it and you would say, you're correct. So under 19, if it's the opposite here, that would work. But yeah, if you applied the parentheses and then you gotta flip that, you gotta change that to the other operator, right? Then that would work for disjunction. And in programming, you know, a lot of times we use higher language to program, but at the low level instructions, what it does is it's looking at your variable and how to utilize the value that you store in that variable, and it would apply the gates to that, right? Because a lot of times I see like students submit programs that would, you know, have loops and conditional statements that would have operators. So what does that really mean? So it's going to go to the location of the variable. It's going to look at that value, and then inside that variable, how it's going to apply the operator, and then on the outside applies another operator. So when you're using the double ampersand, you're going to say if, right, user answer is not equal to 0 and user answer is not equal to 100, then you would have something, a task that's executed. So how does that break down to conjunctive or disjunctive? It's going to go to user answer, look at the value. It's going to operate from the inside, right? Since we and it, right, then it's going to take the value at the other variable, and then it's going to apply in the normal form to be able to check for the condition following the next statement. Okay. So I think the first 3 chapters, you know, the way we want to instruct it is to give you the background on how the computer would operate. And so that way, when you program, you can think about how it should, you know, what's the expectation, right? When you write the statement, what should be calculated in the back. Okay, we have to start thinking that way, because otherwise you're just writing without having a goal or purpose in, you know, the output of your program. Any question? Okay, let's see, what else do I want to touch on? Oh, I still have a lot of time. Anything that you need me to clarify? Let me highlight this. Okay, so just to capture, we talked about different gates and or not, right? We talked about not and, not or, and exclusive or. We touch a little bit on conjunctive and disjunctive normal form related to operators or gates. Okay, so what to expect this week? If you actually take a look at the lab already, we will start writing program in C++. Mainly, I have you either do the example program or use that as a reference to be creating another one. So, you know, it's pretty straightforward. And as we go through, I will introduce you to various STL, how that is used. So next week we'll be using sets. So we're going to go into sets and we'll talk about set as a number, like a number set. We can look at value and we'll talk about Venn diagram and how that ties to programming. Okay. Any question? Okay, I finished pretty early today. If you like to stay on and ask question individually, you're welcome to do so. If you complete everything today, you can submit it, but I did open it so that you can turn it in by Thursday, so it won't be late. But on Thursday, we will meet again and I can go over the lab exercises. You can use Visual Studio or you can use, online compiler. That's fine as long as you can, work with the online compiler. And then, if you want to pre-read, you can read the next. And I post the course schedule on the course plan so you can see. We're gonna skip chapter 5, which is encryption. We're going to come back to it near the end because I wanted to go through probability and countability and permutation and all of that before we get back to cryptography. Okay, and we'll do programming, writing, algorithm for Caesar, cryptography, and Vigenère and such. Okay, any question? Okay, so if you can please type in your name in the chat. I know not all of you did it last time, but that's okay. I do pull the participant list, but I use the chat to verify because some of you don't use your full name when you log on to Zoom, right? Like if you use a nickname, I can't tell who that is. So hopefully I'll be able to see what name you type in the chat and I can determine your attendance then, okay? And then I have updated all your grades. If you receive a grade lower than you expected, it's because I can't find answers on your submitted document. Possibly it's a wrong file. So check your grade, and if you need to resubmit it, you can. So that way I can regrade it. But if you miss unit 1, you can, make sure that you complete it and turn it in so you can get some credit. And then I will have various extra credit in the next week or so. Okay, any question? Okay, we finished 30 minutes early. If you don't have any questions, have a wonderful night. I'll see you here on, what was it, Thursday? And then we'll do the lab then. Thank you.
Hey, Professor.
Good night. Thank you.
Yeah, you're welcome. So
Can
tired.
you hear me? Can you hear me, Professor?
Yeah.
Hey, I just have a question on the assignment that we have today. I wasn't able to see what you got for the first question for describing how gates are represented in the CPU, which comprises of transistors and rules. For some reason, I was having some problem with my connect. Like I couldn't really see your screen. It was just my end. I was having internet problems all day today.
Okay. So I put in the notes also for the transistors, but let me go back to that.
Yeah, I was just downloading it right now too. I was gonna go look for it if you were gonna just get off.
No, I'm fine. I mean, I'm scheduled until, so sorry, I should turn off on the lights in my house. But okay, so basically when you're looking at computer processor, your microprocessors, it just the current processor like AMD Ryzen, your EPYC, your Intel i9, it's just made up of trillion of gates or eventually transistors. There are small transistors that's incorporated, and transistors are made of semiconductor, and semiconductor can be silicon or it could be other type of metal that is what do they call it, where it's not gonna be it can work with higher temperatures. So this is why we're able to includes so many transistor within the actual processor, and then it's, even if it's running hot, it's not going to be able to combust. So now when you're looking at the logic gates, right, it's the way that they illustrate this. So when you're pushing it from the top here, it creates a break. And then when you're pushing it from the bottom here, it creates a close. Okay. So with the break connection, so here what it's saying is that on the left, which is open, and then on the right, which is closed, it's a way that we can illustrate the electrical connection. So when it's closed, you have a closed loop, right, in electrical circuits. So it's going to be closed like this. And now with the pushing from the top, when it pushes through like this, or it's pushing from the top like here, then it's going to be a break in the electrical circuit. So for the AND, right, with the AND, with the construction is that it's still going to be pushed, but it's, so if you have one that's on and the other one that's off, it creates an off. So it would be a fault. So it would be an open. Okay. Where with so A and B represents the two inputs. So you have to have the two inputs in order. So you have this and this right here, right? So in the switches, this would represent the A and the B with the connection established. So both switches are pushed in. So in the case where if you have a 1, that's going to be a 5 volts. And then if you have a 0, that's a 0 volt. So when these two combine, when they are AND together, you would get a 0 as the output. Okay, with the AND. It would be different than the OR, because when you have one that's going to be pushed in, and then the other 0 that's going to be open like this. So in any case, if it's true, it's a push in, you would have a close, a complete connection. So it would be closed right here for the OR, then you would have a 1. So anytime that you have a 1 in the OR, anytime you have a 5 volts, you get an on, you get a 5 volt in the OR. Versus in the AND, anytime you have a 0, it's going to be open, then you would have a 0 as the output. Okay. Does that help, or did I
That
confuse
helps.
you more?
No, it's fine. Do you want us to have Visual Studios, or would you rather have us have something else instead?
It doesn't matter with me. I'm not picky. I would, you know, if you're comfortable using VS, it's fine. You know, with C++ is that you have to bring in the STL that's needed. So there will be time that we would need to have different type of STL. Now, if, you know, Visual Studios is good for C++, but sometimes, you know, my example code might use a different STL, and if you don't have that as part of your package, it might throw an error. But, you know, things like include algorithm, a lot of the times if you have that, that will address some of the things, especially when we work with recursion. But I will let you know. But yeah, VS is okay. I use Replit or repl.it. Which is an online compiler. You can use that as well and cloud all your program. Or if you use CPP, that's okay. There are different online compiler, as long as you can download the .cpp file to save, like for your project or something, that will be okay.
Okay, thank you so much.
You're welcome. Any other questions?
No, that's it. Have a good night.
Okay, thank you.
Professor?
Sure.
I was hoping you could maybe explain to me that last topic we were on, the one with conjunctive normal forms and disjunctive normal forms. Like I just can't figure out how to tell which one's which.
Okay. Okay, let me get back to screen share here. Like number 16 or 17, right?
Yeah.
Okay, so let me go to the notes real quick, and then so I can talk a little bit more about it. So with the conjunction, so think of this as in like these are variables, okay?
Mhm.
And the way that we say a clause or a term. So let's say that you have a variable or an identifier container, whatever you call it, that would be the output of this, A or B, okay?
Okay.
And then another variable that would be the output of C or D, okay?
Okay.
In conjunction or a conjunctive normal form in your CNF, within the term itself, you need to use the OR operator, right? So when you have like one variable or with another, right? And to connect it with the other result, you have to AND it, okay?
Mhm.
Now, also in the case of negation, so when we have not C, if it's not that variable or B, so what it does is it's going to have to find the output of this first by this OR right here, and then the OR right here, and then it's going to AND these terms together. That's going to be, that's going to make it conjunctive. And whenever you see conjunctive, you should think about it's using AND. Okay?
Okay.
The upside down V. So if I'm saying like, for example, on the level of programming, right? Like in, let's say int H, right?
Mhm.
And I would have to end it with int time.
Okay.
Okay. Now, if we operate with as a clause, hold on one second, my laptop's about to run out of power, so I gotta make sure I plug it in. Okay, so in the case of if we wanted to make it conjunctive, we would have to say int time, right? Or int pressure, like that. Okay.
Mhm. Okay.
So, or in the case of if we wanted to say not in age, we can also do it like that, right? Or we can say, or not in pressure. And that's what it really means by A or B or C, right?
Okay.
Now, in the disjunctive normal form, right? Like I want to interpret it in like C++, so hopefully you'll be able to understand. So in disjunctive normal form, it's using the and on the inside and then the or on the outside. So let's say that if we say int price, right? Or int, let's say width, right? Now, if we wanted to calculate this, we can say int width and int height, like that. I'm just, using variable name just for the fact of using variable name. So that would be disjunctive.
Okay.
And in some cases, you would have like int price and int time or int shipping, right? Or int width and int height. So what happens is first it's going to operate this right here where it would AND it inside, right? Get the output, and then it's going to OR it on the outside. So that way it would be a DNF. Okay.
Okay.
Yeah. So how do you determine that? So when you're looking at like the operator from one term to the other, you ask yourself, is it AND or is it OR? If it's AND, likely that it is CNF. If it's OR, then
Okay.
likely that it's DNF. Now on the inside between those two variables before it gets the output, so you know, inside the parentheses, it has to be and while the other one has to be or. So conjunctive, the inside has to be or, disjunctive, the inside has to be and, the conjunctive outside has to be and, or has to be and. So it's just using the other operator, okay? So if we have inside here as and the outside is or, it's DNF, right?
Okay.
And then CNF, the inside is or and the outside is and. So to
Okay.
go back to this question right here, like 17, right?
Uh-huh.
What is it using there?
Is that
Or.
an
It's the or, right? The V is the or. It's the symbol
yeah.
for or. So if we have the or on the inside and the and on the outside, it is a CNF, right? Or
Oh.
inside and outside. So if we have, so this is, basically this is, right? Basically that is, I'm gonna recopy this, sorry. Basically this really means that it is not X or Y or Z and X or Y or not Z. It's not negative Z, it's not Z, it's the inverse of, or it's the opposite of Z.
Mhm.
Okay, so now, right? So that would be a CNF. CNF, why? Because it uses or on the inside and on the outside. So it ors within the terms, and then it's and outside of those terms.
Okay. And
Okay.
then the other one would just be the opposite.
Well, the other one is tricky because here it's using the or, right? But
Okay.
on the inside, it's using the or. So it does not meet the DNF or the CNF criteria.
Okay.
Yeah, because so see how this one it uses the and, okay, that first part is okay, but then when we get
Mhm.
here, right, it's using or on the inside, so it's kind of like no. So if this alone would be okay, that would meet some criteria for the CNF, but then because it's using this right here and it's using this right here, so it's a mix, so this is neither DNF or CNF. Okay.
Okay.
It has this and the other one. So when you see this right here,
Uh-huh.
okay, so this is or inside, so that doesn't work, and then it's and on the outside. So
Okay.
up to here, we would say that it would be DNF, but because of this, it cannot be. And or connect operators is used to connect the terms, so it's not a CNF. Okay. All right. And if you look at 19, 19 uses what? And, right? It's and on the outside, it's or on the it's and on the inside, it's or on the outside. So in general, this is a DNF so far, right?
Uh-huh.
But
Yeah.
then when it gets here, it does the and the and again, so it does not completely meet the DNF criteria. So it has like half and half. So it's neither DNF or CNF.
Okay.
Yeah. It's just a little tricky. So if you see inside a parenthesis, if it's, you know, it's, and outside has to be the other gates.
Okay.
Does that
Thank
help?
you. Yeah, thank you so much.
You're welcome. It's just reading the symbol sometimes is confusing.
Yeah, it makes perfect sense now.
Okay. Other questions? No other questions?
Okay, have a good night, Professor. Thank you.
All right, good night. Take care. Have a good one.
You too.
Thank you. Eric, you okay? You have any questions? Okay, no question? Okay, Eric, I'm gonna take off. I'm gonna sign off if you don't have any questions so I can wrap up the cloud video and put it into the course. If you have any questions, you can shoot me an email or a message, okay? Have a good night.